In this video, we've got a product of sine and cosine, and they have different exponents. So let's see what we can do here to make this something we can calculate. Well, one of the things I notice is I have an odd number of cosines. So what I'm going to do is I'm going to split one of those off, and I'll have cosine squared x, sine squared x, cosine x, dx. Now, initially this may not look like much of an improvement, but let's see where we're going to go with this. Now, I know that the derivative of sine is cosine. So I could possibly, at this point, let u equal sine x, and then du is cosine x dx. That would take care of this piece here, and that would become a u squared. This we don't have quite a substitution for yet, but what we're going to do is we're going to apply our Pythagorean identity that says cosine squared x is equal to 1 minus sine squared x, and put that in there. So we have 1 minus sine squared x times sine squared x cosine x dx. Now we can do our substitution, because here is exactly our du. Those signs are going to become u's, and we'll have 1 minus u squared for this part. Sine squared x will become u squared, and cosine x dx is exactly du. We now have an integral all in terms of u. Pretty basic integral, actually. We're going to distribute the u, and we'll have u squared minus u to the fourth du, which we can do piece by piece. So we get u cubed over 3 plus u to the fifth over 5 plus c. And our last step is to substitute back in our sine. So we have sine cubed x over 3 plus sine to the fifth x over 5 plus c. So there's a lot of variations of this when you have a product of sine and cosine and their powers. One of them's odd, one of them's even, or both of them are even. This is just one particular case, but it gives you something now to look for. Splitting off that cosine, or sine if it was the other way around, and doing a u substitution of just sine, not sine squared or anything like that.